Alright, so ladies and gentlemen, let's take a look at a conservation of energy problem. A cart moving to the right passes point 1 at a speed of 20 meters per second. Right away we want to go ahead and write down our list of knowns here and label our diagram. Let g equal 9.8. What is the speed of the cart as it passes point 3? Part A. So really what we have to understand about this problem is that it's about energy, because we know that the amount of energy we start with here at point number 1, the total energy, right, E total, has to be equal to the total energy over at point 3, as it's called in the problem. Now, if you are at a height of 0 at point 1, then we can say for certain that we have 0 joules of potential gravitational energy. That's a G. Up here, since we now have a height associated with our position at point 3, that means that we are going to have to account for both kinetic energy and gravitational potential energy at point number 3. So what we can say is that in this problem, since we have ignore friction as one of our big hints, that's telling us that all the energy is going to be conserved. So this problem really is about energy. So as we take a look, we have no potential, it's all kinetic at point 1, and we have kinetic and potential energy at point 3. So now when the question says what is the speed of the cart, we're going to go ahead and set up our conservation of energy equation. Now 39 and 40 are tied together, so just ignore all the 40 stuff for the moment. So as we take a look at part A, for number 39 up here, and we look for the speed of the cart as it passes point 3 here. We'll just call that V3 since it's the velocity at point 3, and we're trying to solve for that. So given the idea that the energy here is equal to the energy over here, I should say the total energy at point 3 is equal to the total energy at point 1, we can go ahead and set up an equation for that. We can say all the energy at point 1 is equal to all the energy at point 3. And so as we take stock here, we say, all right, well, we have kinetic energy at point 1, so K1 I'll call it. And at point 3, as we discussed previously, we have kinetic energy, so I'll call it K3. And we also have gravitational potential energy. I'll call it UG3, just at point 3. Don't let the subscripts throw you off. It's just a good way to stay organized. But the nice thing is here, let me readjust for you here. Yeah, still like that. There we go, that's better. What we can do now at this point is go ahead and blow out these equations. So since we know that kinetic energy is 1/2 mv squared, kinetic energy again is 1/2 mv3 squared, and the potential energy is mg. Some people will write it delta y, some people will write it as h. I'll go ahead and write delta y for this one, or the change in height. So we can go ahead and plug in all our numbers here. Now the interesting thing about when you have total mechanical energy, that's defined as how much kinetic plus potential energy you have. Those two fall under the umbrella of total mechanical energy. What we see here is that the masses actually cancel because we have a mass here, we have a mass here, and we also have a mass right here. So that's convenient and necessary because the problem didn't give us the mass in the first place. So that's nice. As we continue forward here, we take 1/2 of V1. Now it told us right back here to our diagram. That's why it's so important to label your diagram before you start. Our initial velocity up there is 20 meters per second. Go ahead and square that. We have 1/2 of the velocity at point 3 plus g. We'll use 9.8 meters per second squared. And our change in y, as you can see from the diagram, we started at a height of 0. We're now at a height of 10. So I'll go ahead and plug in 10 meters there. All right, so now the rest is just algebra, which is kind of the boring part. But if you can set this problem up in the correct fashion, as we see here, then you'll be in good shape to continue forward. So I'll kind of fast forward some of the algebra for you here. Let's see, we have 20 squared would be 400. Take half of that, you get 200. Now I'm not going to write joules because we canceled mass, so we're in some weird unit right now. So I'm going to practice some bad habits and not put my units, but just hang with me on this one. All right, equals 1/2 V3 squared plus, this is going to be about 98 over here. The nice thing, these numbers work out really nice. You would subtract 98 from both sides, and it looks like on your screen you're running out of room, so I'm just going to go ahead and continue this problem right over here. So you hang with me on that one. All right, so that would get us 102 on this side equals 1/2 of V3 squared. Of course, if you want to solve for that, this is 3, sorry about that. If you want to solve for the V3, you'd have to multiply both sides by 2. All right, that would get us 204 equals V3 squared. And of course, the final step is just to take the square root, and we're going to get a number. I didn't bring my calculator to physics class because I'm an idiot. So I'm going to take the square root of 204, and of course, that would be our final answer for velocity. Give me 1 second, I'll find the answer for you, for all you type A people that need to know you got the right answer. And the suspense was killing me, it's over. Our answer here is 14.28 meters per second. That's telling us how fast are we going at the top of this hill. Tune in next time for a blended, what if we have kinetic here and potential here and kinetic here and potential here. You see, this problem is nice and easy, it's pure, because we have only kinetic here, and we have a blend of kinetic and potential here. Now, as you can imagine, let's say I said, hey, how fast were you going at the top of hill 2? You know, it wouldn't be too far of a stretch. We could say, oh, kinetic at 2 plus UG potential at 2 would have to equal to the total energy anywhere else.